Let's read the Ethereum Whitepaper as it was published in 2013. It's quite a long time ago now. And even before the project launch in 2015. I heard it was a really good paper. And I happen to have not read it. Very surprising, actually. So better later than late than never, and let's get started. A next generation smart contract and decentralized application platform. Satoshi Nakamoto development of Bitcoin has been here as a radical development money. Interesting value and no centralized issuer controller. However, another argument important part of the Bitcoin experiment is the underlying blockchain technology as a tool of distributed consensus. And attention is rapidly starting to shift to this other aspect of Bitcoin. Commonly cited alternative applications of blockchain technology include using on-blockchain digital assets to represent custom currencies and financial instruments called coins. Okay. The ownership of an underlying physical device, smart property, non-fungible assets such as domain names, Namecoin, as well as more complex applications involving having digital assets being directly controlled by a piece of code implementing arbitrary rules, smart contracts, or even blockchain-based decentralized autonomous organizations, DAOs. What Ethereum intends to provide is a blockchain with a built-in fully-fledged Turing-complete programming language that can be used to create contracts that can be used to encode arbitrary state transition functions, allowing users to create any of the systems described above, as well as many others that were not yet imagined, simply by writing up the logic in a few lines of code. Okay, so what he says here, maybe he's going to get into more details later, but he says that Bitcoin has two important things. It has the concept of the currency that is not centralized, that is not controlled by a government or central authority, and the blockchain. So that is interesting. The blockchain thing truly became independent from the currency aspect of Bitcoin. And with these color coins is a project where basically, actually, I'm not very familiar with this. Namecoin is built on top of Bitcoin. So one of the ideas they had was that there is some space that in the Bitcoin transaction you don't have to use, or you can use, but you can use arbitrary. And they use it to encode additional data. So this is similar to hiding a text under a text, right? So sometimes you have a poem, or you have a letter between two people, and there's a secret code in it. For example, you could read the first letter of each sentence, and that makes another message. So the idea is kind of similar here. In Bitcoin, normally it's done for encoding transactions that send currency between parties. But you can use, for example, the address itself as a way to represent some information. Naturally, this is not the intended way of Bitcoin, so it's not very efficient. So that's why I guess he wanted to create Ethereum. So there are a lot of limitations, and also it's not efficient in terms of like byte use and of course then money spent, because you have to mine these transactions. So a bit of history. The concept of decentralized digital currency, as well as alternative applications like property registries, has been around for decades. The anonymous eCash protocol. Okay, so history, that's super interesting. I think that the idea there that there was some guy called B-Money and Hal Finlay introduced the concept of proof of work, and with Adam Back. So these guys are very famous guys in the cryptocurrency. I think Adam Back is now a CEO of blockchain. Which hires a lot of the Bitcoin core developers. Hart Finlay was worked with Satoshi in the early days. Unfortunately, he passed away a few years ago. But he's probably the guy who has the second biggest stash of coins, of Bitcoins, after Satoshi. Okay, so now he's talking about the mechanism behind proof of work was a breakthrough in the space because it simultaneously solved two problems. First, it provided a simple and moderately effective consensus algorithm, allowing nodes in the network to collectively agree on a set of canonical updates to the state of the Bitcoin ledger. Yeah, so this is basically like the mining protocol. Second, it provided a mechanism for allowing free entry into the consensus process, solving the political problem of deciding who gets influence in the consensus, while simultaneously preventing cyber attacks. It does this by substituting a formal barrier of participation, such as a requirement to be registered as a unique entity. The weight of a single node in the consensus voting process is directly proportional to the computing power that the node brings. Since then, an alternative approach has been proposed called proof of stake, calculating the weight of a node as being proportional to its currency holding and non-computational resources. The discussion of the relative merits of the two approaches is beyond the scope of because this is a very there's a lot of discussion and argument against this. So proof of work. Okay, so there's no, it doesn't mention proof of work as of yet. So proof of work means that in order to have more weight in the Bitcoin network. So when you have a decentralized system, so you have a bunch of guys who want to participate, but you still want to have one version of the truth. So what do you do if one guy disagrees with another guy? So the typical case in Bitcoin is if one guy decides to double spend. So he has one Bitcoin and he simultaneously creates two transactions spending the same Bitcoin. So in this Bitcoin terminology, it's more like he only controls one endpoint that has one Bitcoin, so one account that has one Bitcoin, and he spends from that endpoint to two different addresses at the same time, right? So he creates two transactions and he pushes them into the network. So normally the system can only work if only one of these transactions will take place. So which one will take place, and how Bitcoin maintains the only one version of the truth? So what he says here is that Bitcoin uses proof of work, and actually Ethereum also uses proof of work, which means that in order for the transaction to be finalized, it would have to be part of the block, one of the block of the blockchain. And to enter the blockchain has to be valid, and for it to be valid, it has to contain proper nonce. Nonce is an arbitrary number than whoever creates the block can choose, right? So without any restriction, except like the size of the nonce. And so how does it help? In itself, it doesn't really help anything. But the idea, though, is that with this hash cache, right? This guy has the idea that if you then take the hash of the block, so including the nonce, so actually not the entire block is hashed, but conceptually it's as if the entire block is hashed. If you hash the entire block, you will have a value. And if you require that value to be below a certain limit, so it's the difficulty of the network. So let's say that the hash has to be lower than 100 billion. Then that puts a restriction to what nonce you can use. To remind you, the hash value is really harsh number. So 100 million is actually nearly nothing. The hash value is a number that has 256 bits, and in alpha. So if you talk about the range that a hash can have, this is more like like this. Right? So 100 million will be just barely here. This is 100 million. Power 77. So a million is only 6. So it's more like a difficulty is a million, 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 something like that, right? But if you require that, then the nonce cannot be any nonce. And since the hash function is really one way, so there's no way for anybody to take arbitrary hash and then figure out which nonce led to this hash. It boils down to trying them out using resource, electricity, compute power, to generate hashes, and hope that the hash you find is eligible, is below the threshold. And the lower the threshold, so again, your hash has to be below the threshold. So the lower the value, the harder it is. So the lower the threshold, the harder the difficulty is. This means that you would have to spend more and more power. Even though, like technically, you could be very lucky and then only use the first try you get it. In terms of probability, this is very unlikely to happen. So right now, the difficulty in Bitcoin is so high that it is kind of equivalent to finding a single grain of sand in the entire world. So that tells you how much efficient these nodes, these miners have become, because they literally hash a petahash per second. So peta is 12, I think. Let's see, petawatt. Why is it taking so long? 15, that's even more than I thought. So 10 power 15 per second. You can see that this is still way below 77. It's not saying that the difficulty is like 1 out of 77. So I think we can go and look at the Bitcoin current difficulty. But I think it has come down a little bit. So yeah, you have charts that shows you the current difficulty of the Bitcoin network, and you need to know that it readjusts every 2016 blocks in order to keep roughly one block every 10 minutes. So that's one way to do it, and it's actually a way that arguably spends a lot of energy. So people have suggested proof of stake, which actually spend way less energy, nearly zero in comparison. But there are concerns that it is not as safe. Okay, so then he talks about Bitcoin as a state transition system. So state is a term that is pretty common in computer science. A state is basically whatever your system has currently as data. So it's as opposition to code. So code is something that you will execute. So to take an analogy, if you have a recipe for a cake, the recipe is the code, because you can reuse the same recipe and make many cakes like a factory. But you have to use different ingredients, right? And so your ingredients would be your data, and it would transform eventually, going from the initial state, which is a bunch of raw ingredients like eggs, flour, and so on and so forth. And as you apply more and more steps, you do more and more the steps of the recipe. You get closer to the final state, which is the cake. But you will have obviously a bunch of intermediary states. Will be like you have beaten the eggs, you have sifted the flour and stuff like that, right? So in Bitcoin, you have the notion is that every change of state is encapsulated by a transaction, and this is the only thing that actually can change the state of the network. And so let's take a look. From a technical standpoint, the ledger of a cryptocurrency such as Bitcoin can be thought as a state transition system. Right? So I think the emphasis here is that things do not happen at random. If you have a known state and you have a transaction, so you know what kind of transformation you're supposed to do, then you will have an output state. And if the transaction it doesn't follow certain rules, then the transaction will be reverted. It will be so first, basically, to take the same analogy as the cake. If you have the recipe says you have 6 eggs, but so you are supposed to do a transaction with cracking 6 eggs. That's what the transaction says, the recipe says. But you turn out to only have 5 eggs. Then it's not like you're gonna crack 5 eggs and then realize that, oh, oops, I'm stuck here. I have to go. I don't know what to do. So it's all or nothing. Either you crack no eggs, or you have 6 eggs and you can proceed forward. So that's a pretty important thing in finance, because many of the transactions have to be atomic. This is a property called atomicity. So, for example, if you send money to another person, and you don't want to credit that account before you. So you want to send like $1,000 to that person, so and you credit that account before you realize that your account doesn't have, the bank credits that account before the bank realizes that you don't have enough money. Then it's possible for that person to see the money it has received and spend it immediately, right? So the bank should not credit that other person's account before it debits your account. So these two operations has to conceptually happen at the same time, even though it's not obviously nothing happens exactly at the same time. But as an outside observer, it's either all or nothing. It's either that person has the $1,000 and you have $1,000 less, or nothing happened. So in a standard banking system, for example, the state is a balance sheet. A transaction is a request to move X from A to B, and the state transition function reduces the value of A account and increases the value of B account. So it's actually exactly what I was saying. If A account is less than N, the transaction returns an error, right? So that's what he's saying. If you don't have enough money, you have an error. So it's either the new state or an error. You don't have a state where some money was created or some money disappeared. The state in Bitcoin is a collection of all coins, technically unspent transaction output or UTXO, that have been mined and not yet spent. For each UTXO having a denomination and an owner, defined by 20 byte address, which is essentially a cryptographic public key, a transaction contains one or more inputs, with each input containing a reference to an existing UTXO, and the cryptographic signature produced by the private key associated with the owner's address, and one or more outputs, with each output containing a new UTXO to be added to the state. So that is actually quite a lot to parse here. I don't think he made a diagram. Right, so we have to imagine what's going on here. So first he says that one interesting thing is let me see, where is this? Okay, so that the money comes from mining, right? So you don't have Bitcoin created if you go to an exchange and they say, okay, buy Bitcoin, they are not creating Bitcoin. And if somebody tells you that they have a way to create Bitcoin without mining, that is 100% a scam. It cannot be created besides mining. So this is mining is a process that maybe this talks about later, probably at one point. Yeah, mining is incoming. You will talk about mining, but actually this is a way to reward the people who are spending energy to calculate to find these nonces and to calculate these hashes in order to ensure that there is only one version of the truth, the blockchain. Well, technically there are forks, but there's only one version that lasts a long time. So when a miner gets this, he gets to receive this mining reward, because in the block you will have a bunch of transactions. So transactions are very similar to this stuff. It says send from a bunch of sources to a bunch of destinations, right? So there should be equivalence between balance between source and destination. You definitely cannot send more than you have. So the destination balance, some amount that you send to the destination, should be lesser or equal to the sum that you are sending. So not equal, because there's a minor fee, and that difference is then sent to the miner, right? But in terms of ecosystem, all the Bitcoin doesn't really care, and Bitcoins do not disappear. So if you sum all the transactions that are like this, you will have the same number of Bitcoin as defined by the schedule, right? So schedule meaning that every block you will have a known reward, so a known creation, known amount of Bitcoin created. Cannot be more. It could be less actually, because technically the miner can mess up. But assuming that nobody messes up, this amount is known. So it's a matter of redistribution of this Bitcoin between people. And these transactions, so the way they work is that you send money to you take from these unspent transaction output. So it's really exactly what is meant here. The terms is kind of obscure, but it's kind of like a exact definition of what it is. So you have the transaction, and transactions has input, and then it has outputs, right? And these outputs, either they become the input of another transaction, or they are still there. So if they are still there and basically unused yet, they are unspent. So you can only connect a new transaction, if you connect it to an unspent transaction output. So it's like a game where you have you connect the dots, right? Where you connect, and then you at one node, one spot, and you want to connect to the next dot. You are not allowed to connect to a dot that has already been connected to another dot, right? So that's the rule of the game, and you can take one dot and then a bunch of dots. So take like 3 dots that are unspent as input, and produce 5 dots, right? So, and these 5 dots will be unspent transaction outputs. So the idea here again is that you're only allowed to use dots that have not been used before. So if you want to take an analogy with money, this is like if you had a bunch of piggy banks. If you have tons of piggy banks, but in order to pay somebody, you can't take the coin from a piggy bank. You have to smash it. So you smash the piggy bank, you take all the money. And then if you don't have enough, you smash the piggy bank, and so on and so forth. You collect all that money, and then you create another. You can create well, not create, but you spread it into other new piggy banks. And these new piggy banks, you can give it to somebody else, the guys that you are paying, or you can keep it, right? So why would you keep something? Well, it's most of the time, well, nearly all the time, you would not have the exact value. So if you have a bank, you have $1, 1 Bitcoin, 2 Bitcoin, then the sum is 3 Bitcoins. So you have one piggy bank, 2 piggy banks, one with $1, the second one with 2 Bitcoin, and you have to pay somebody 2.5. But it's more than 1 piggy bank. So the max you had was 2 Bitcoin. So you have to spend both piggy banks. So you have to smash them open, but then you have 3 Bitcoins. So what you would do is you will create new piggy banks, one with 2.5, one with 0.5, assuming you don't pay a fee. And then you will give that piggy bank to the other guy. The first one will have 2.5, and then you will keep the one that has 0.5. So you can see that it gets pretty hard to manage, right? You have potentially all these UTXO. Let's call them as they are. You have a bunch of these UTXOs that you know how to spend. Only you know how to spend. But you may end up having so many that it's hard to manage. So that's why you need a software wallet that basically manages all this stuff, right? But that's the model for Bitcoin. And the second thing he says here, okay, so I said transaction contains one or more inputs, yes, and each input contains a reference to an existing UTXO. Yeah, we know that. And then what does he say? And the cryptographic signature produced by the private key associated with the owner's address. So that's the thing we need to talk about. Here is that when you create a piggy bank, right, you also basically tell you mark the bank with the public key, right? So it has some kind of label, and that public key is associated with a secret key. So keys come in pairs. You can create keys very easily, but you will have a pair. You can create pairs of keys very easily, and you will have a public key and a secret key. So they go together. If you lose the secret key, you cannot use it. You cannot use the pair. And actually, if you lose the public key, then you cannot use the pair either. But luckily for you, going from a secret key to public key is very easy. So no problem. Actually, if you have a secret key only, you can compute the public key, and then you can use the pair. But if you lose the secret key, now no dice. You have only the public key. There's no way to get a secret key from it. So public key, as its name implies, means that you can give to anybody. There's no danger of figuring out the secret key out of it. So you label your piggy bank with the public key, but in order to spend that piggy bank, in order to smash it, the Bitcoin protocol will require you to show that you have the secret key by making a signature, and the signature will be verified by the other nodes in the network to match that public key. So technically speaking, it's not exactly the public key, so that's why there's a little caveat here, because it's such a hash. But for all manner of purposes, this is equivalent to saying that the piggy bank has the public key. And you cannot make a transaction. You cannot say that you are using that piggy bank, try to smash it, unless you have the secret key to sign the transaction. And that's obviously enforced by the Bitcoin system. So if you try, then you will get an error, right? One would the system would try to apply a transaction. It would not transition to the state where the UTXO will be spent, but it will return an error, and your transaction will be reverted. So it's as if it never happened. So I think we managed to understand this stuff. And then we go here. So this is the state transition function can be defined roughly as follows. For each input in TX, if the reference UTXO is not in S, return an error. Alright, so if you have a transaction but you're pretending to spend a UTXO that doesn't even exist, then bye-bye, right? And if the provided signature does not match the owner UTXO, then also bye-bye. So first, we need to find the piggy bank, and second, the signature has to match the public key that is on the piggy bank. So very, very natural, normal. If the sum of the denomination of all the input UTXO is less than the sum, so if you are basically you want to spend $1 but pay $2, then no, that's not correct either. You're spending more than you have, And if all of that is okay, then you have transitioned to the next state, where all the inputs to UTXO are now used. So they are not UTXO anymore, because UTXO should be unspent. Now they are spent, so they should be removed. And then the new outputs that you just created are UTXOs. So you add these guys as new UTXOs. The first half of the first steps prevents transaction senders from spending coins that do not exist, of course. The second half of the first step prevents transaction senders from spending other people's coins. And the second step enforces conservation of value. Okay, so that's pretty clear. In order to use this for payment, the protocol is as follows. Suppose Alice wants to spend 11.7 BTC to Bob. First, Alice will look for a set of available UTXO that she owns that totals up to at least 11.7. Realistically, Alice would not have to get exactly 11.7 Bitcoin. Say that the smallest she can get is 6 plus 4 plus 2, 12. She then creates a transaction with those 3 inputs and 2 outputs. The first output will be 11.7 BTC with Bob's address as its owner, and the second output will be the remaining 0.3 BTC change with the owner being Alice herself. So that's exactly what I was saying earlier. So mining. So let's take a break now and we'll come back with mining.